As we already know from the diffusion equation, the implementation of the full implicit method, it requires the matrix representation. So here, that's what we are going to analyze. That's going to be the matrix representation for the fully implicit method that's applied for the Black-Scholes equation. So first, we're going to start with the finite difference representation we have just described. This is the one. Or we can also write the same one in this way. Basically here what I've done is basically I have substitute these A, B, C functions that appear here, taking the ones that they're coming from the Black-Scholes equation. So in this case that sigma, which is the volatility, and the interest rate, it's independent of time. These coefficients of these functions are going to be independent of the J index. So, for example, the A evaluated at nj plus 1 is going to be 1/2 sigma squared s squared, which in this case is going to be n squared delta s squared. On the other hand, the B, which is evaluated at index n and time j plus 1, is going to be r times s, which is n times delta s, and the C1, which is evaluated at n j plus 1, is going to be minus r. Okay, these are the ones that we have considered when substituting and getting this expression, but the two are equivalent. But in order to, as you can see, the coefficients of this expression, these coefficients are multiplying, these b functions are quite big, and so in order to make the matrix representation to look more simpler, we're going to redefine another functions here, another coefficient actually, which are these capital letters A, B, C, which in this case is evaluated at n and time j. And these are going to be the following. So this, the one that we are going to call it, so the one here, we're going to call it A. In this case, A is going to be evaluated at n and time j plus 1. Okay, this is the one. Another one is this one. In this case, this is just this one. We're going to call this one, we are going to call it B, which again, this B is going to be, it's evaluated at index n and time j plus 1. And another one, this one, included this minus coefficient, this one is the one that we're going to call C, with capital C, evaluated at index n and time j plus 1. So these are the new coefficients that we're going to define. And considering that, then the matrix representation that we do have as a function of this coefficient that we have just defined is given by this expression here. And so once we do have here, just remember that this n, which appears here, it goes from 1 to ns minus 1. So we have like ns minus 1 equations like this one that we need to apply for all different j times. And remember that we were doing everything which depends on j plus 1, we're going to bring that to the left. And everything which is in this case depends on j, we are going to bring that to the right. So here, these ns minus 1 equations, we can write it all at once, just using the matrix representation. That would be the matrix representation for all the sets of these equations. For example, applying that for n equal 1, we do have like a1 at the value of this time times b0 plus 1 minus b1 times b1 plus c1 times b2. This is the one which coming from multiplying this row here times this column here. There are just three elements, the ones coming from the product of this one with this one, then we have this one with this one, and this one with this one. So this is the three products that we do have. And that will be the first one. And doing the same, we have all different ns minus 1 equations that can be written in this way. Okay, in this way. So as you can see, again, this matrix here is non-square matrix, and we have this column here, this column vector here corresponding to a b values evaluated at time j. We have the number of rows we have here is ns minus 1, while the number of rows we do have here is ns plus 1. So Here in this matrix representation, the matrix has ns minus 1 rows and ns plus 1 columns. It's not square. And this is a representation of the ns minus 1 equations and ns plus 1 unknowns. Because actually here, the unknowns are actually these ones. These are the unknowns. Yes, and this, so because just supposing that we do know the values of these functions evaluated at the previous time step, we do want to know which are the values of the options at the next time step. These are unknowns, so we have the number of unknowns are ns plus 1. And the two equations, okay, that we are missing, they are coming from from the boundary conditions, the same we had for the diffusion equation. So using that equations that we are going to convert this system of equations into a system of equations involving a square matrix. So we need to transform that matrix representation in order to get the square matrix from the matrix we have just defined. So the aim is to write the system of equations in this way. So a matrix, a square matrix, evaluated at time here j plus 1 times multiplying this v vector evaluated at j plus 1, then plus some column, and this column we're going to call it again this r vector that will be evaluated here at time j plus 1. It's going to be equal to the values of v, which is going to be a v vector, in this case evaluated at time j. So from non-square matrix this one, and a vector this one, where all the details of the boundary conditions were included principally here, but also can be also included in this matrix M. So once we have that, then it will be easy to do what we actually did for the in the implicit method in the diffusion equation. Basically, just taking that, we need to bring this column vector to the right, and that's what we have. This is v evaluated at j minus r evaluated at j plus 1. Everything here, all the matrices we do here on the left we're going to use the subscript, or sorry, the superscript here, L, in order to say that these are the matrices that we have here on the left. So we have here, and then these, so we have already bring this to the right, and then we have this matrix here that's multiplying this v at time j plus 1. We'll go to the other side with inversion of the matrix. So we do have that v evaluated at j plus 1 is going to be the inverse of the matrix here on the left evaluated at time j plus 1 minus 1 times this one. So if we already know this matrix, if we already know this matrix, this column vector R, and this is the values of the option that we already got in the previous time step, then in this way, considering that transformation, we'll be able to get the values of the V option values evaluated at the time j plus 1. So here the aim will be to include and how to insert the boundary conditions, in this case associated to different type of options in the Black-Scholes equation, in the matrix representation for this fully implicit method, and that's what we are going to do next.